Okay, so let's see how we're going to plug this into our graphing calculator. So a couple of settings we need to adjust. A, we need to adjust the window settings to try and reflect the domain that we're working with. And B, you want to make sure that we're in radian mode. So mode should be radian. For window settings, you'll notice that my graph is going from negative 2 pi to positive 4 pi. So I'll go from window settings. So x minimum is negative 2 pi to positive 4 pi. And the scale factor this time is I've got subdivisions at pi over 2 units. So pi divided by 2. I'm going to change the scale factor to pi over 2, x scale, which means all the subdivisions along the x-axis are at pi over 2. The y minimum I had was at negative 2. The y maximum I had was at positive 2. And the y scale factor is 1 still. Okay, so that adjustment I need to make to the window settings so I get the graph that I can sketch over. And then y equals, I want to first graph cosine of x, right? Cosine of theta, cosine of x, same thing. And you'll notice the cosine of x function will give you the same graph that we came up with earlier. Okay, now we want to see how this graph is going to be changed. We predicted that y equals 2 cosine of x is going to be vertical expansion by 2, which means the amplitude is going to change to 2. Let's see if that actually happens. 2 cosine of x. Let's graph that. Right. Did you notice that the amplitude changed? Yeah, the amplitude changed to y equals 2 cosine of x. Okay, and then let's try the other one, y equals 1/2 cosine of x. So I'll delete this one over here. Leave the original on there. So y equals 0.5 cosine of x. And you look at that, right? 1/2 cosine of x is going to be the ones where the amplitudes got cut in half. So we'll copy these over and we will see what happens if we change some other parameters. So the parameter in front is going to control our amplitude. Let's go ahead and copy these over now. So once again, that's original function. We'll draw the first transform function y equals 2 cosine of theta in green, in which case all the y values had gotten doubled. So 1 became 2. 0 stayed 0, negative 1 became negative 2, 0 stayed 0, 1 became 2, 0 stayed 0, negative 1 became negative 2, 0, and 2. So the graph changed to this. Okay, it got stretched vertically by a scale factor of 2. Similarly along this side. So that was our first graph, y equals 2 cosine theta. Our second graph, I'll put it in red. The 1/2 cosine theta is basically going to show that all the y values get cut by a half from the original graph, not from the new transformed graph. The original graph is blue, so all the y values get cut by a half. So a half, 0, a half, 0, a half, 0, a half, 0. Oh, no point there. A half. So your graph is going to look something like this. All the y values are going to be cut by a half. And of course the blue one I didn't label is the original. Okay. Similarly, can we make predictions on the second graph now, second set of graphs? By the way, are we okay with this? Yeah, we got these down. Okay, just some key points you're highlighting and you're connecting those dots. Take a look at the next example. We're going to put this all together in a few minutes here, but I just want to have us try a few more examples. Let's take a look at example number 4. In example number 4, something else is different. Something else is happening. We're comparing sine of theta with sine 2 theta and sine 1/2 theta. Let's make some predictions on that. So one will be sine 2 theta. What prediction will you have for sine 2 theta? Think back to transformations again. Horizontal compression by 1/2. So you're saying it's going to be horizontal compression by 1/2. Good. So the sine graph's going to get squished horizontally. And then what about the second one? I'll put that in red. Sine of 1/2 theta. What do you expect there? Horizontal expansion by 2. Right, so let's see what actually happens and if our predictions are correct. First things first, before I go on the graphing calculator, let me graph my original function. So original function I'll label 0, 2 pi, 4 pi, pi, pi over 2, 3 pi over 2, 5 pi over 2, 3 pi, 7 pi over 2. Similarly, negative 2 pi, negative pi, negative pi over 2, negative 3 pi over 2. Hopefully you're okay with the labeling part of it. I'm just going up by a scale factor of pi over 2 each time. Pi over 2, 2 pi over 2, which reduces to pi, 3 pi over 2, 4 pi over 2, which reduces to 2 pi, 5 pi over 2, 6 pi over 2, which reduces to 3 pi, and 7 pi over 2, and then 8 pi over 2 reduces to 4 pi. Okay, original sine function starts off at 0, 0, ends at 2 pi. There's another 0 right in between at pi. And then in between those two zeros is your maximum point of 1. So it's 0, 1, 0, negative 1, 0. That's how sine function behaves. Okay, it goes from 0 to maximum to 0 to minimum back to 0 again. Similarly, starts at 0, goes to maximum, goes back to 0, goes to minimum, goes back to 0 again. It's going to keep on going in this pattern. Okay, similarly, negative 2 pi, 0, maximum, 0, minimum, 0. That's original function y equals sine theta. Now we want to graph the transformations. So let's see what the transformations are going to look like. Similar idea on the graphing calculator. I'll leave the scale the way it is. I'll just go ahead and clear these. I'll use y equals sine x as my original function. When I graph it, you'll notice that the graph that we get is going to be the same one that we've graphed over here. Okay, time to look at the different transformations. Y equals sine of 2 theta, which means y equals sine of 2x. We had said that the graph is going to be horizontally compressed by 1/2. Let's see if it in fact does. There you go. It's hard to see, but you'll notice that in original function y equals sine theta, we can fit in two full rotations into our domain on the right hand side and one rotation into our domain on the left hand side. If you look at this now by itself, if I take this graph out, only look at the transformation graph, you will notice that now you can fit in 1, 2, 3, 4, twice as many rotations on the right hand side, and 1, 2, twice as many rotations on the left hand side. It got compressed by a scale factor of 1/2, which means you're fitting that many more graphs in the same domain. Zero to 2 pi became 0 to pi, right? 2 pi to 4 pi became pi to 2 pi, and so on and so forth. And then it kept on going because it's repetitive. It filled in the gap. So when we copy this over, you just got to take all of our x values, cut them in half. So 0, 0 stayed the same. This maximum was at pi over 2. It's now going to be at pi over 4. Half of that. The next 0 was at pi. It's now going to be at pi over 2. The minimum was at 3 pi over 2. It's now going to be at 3 pi over 4. The 0 was at 2 pi. It's now going to be at pi. So that big rotation from 0 to 2 pi reduces down to this rotation, 0 to pi. Similarly, the next one, the one from 2 pi to 4 pi, half of 2 pi is 0, so you got a 0 here. Half of pi over 2 is half of 5 pi over 2 is 5 pi over 4. So 5 pi over 4 is up here. So 5 pi over and 1. 3 pi, half of 3 pi is 3 pi over 2, so your next 0 is over here. Half of 7 pi over 2 is 7 pi over 4. And then half of 4 pi is 2 pi. So your next rotation ends up right here. And then with the same continuous pattern, you can fill in the gaps. Maximum 0, minimum 0. Maximum 0, minimum 0. Because it's periodic, it's going to oscillate this way. Similarly on the back end, right? So from negative pi to 0, it's going to be 0, maximum 0, minimum 0. Similarly from negative 2 to negative pi, 0, maximum 0, minimum 0. So 0, maximum 0, minimum 0. Right? So this is the first one here, y equals sine 2 theta. Similarly, we can take a look at y equals sine 1/2 theta. We had said that 1/2 theta is going to be a horizontal expansion by 2. So if I compare that to the original one, here's the original one again. I'll clear the second one here. So here's the original. Here is y equals sine of 0.5x. You'll notice that it's sort of been stretched. Now I'll turn the original one off again for you to see that carefully. Instead of having 2 rotations, you now only have 1 rotation. It's been stretched. Right? That 1 rotation is taking up 4 pi units rather than taking up 2 pi units. Similarly, on the left hand side, you're only getting half a rotation because you don't have enough space to fill in that full rotation in your domain. Right? So when we copy this over, this is what it's going to look like. 0 stayed 0 on the original function. On the original function, we had a 0 at pi. It now became a 0 at 2 pi. The one that was at 2 pi became a 0 at 4 pi. There was a maximum at pi over 2 on the original function. That maximum is now going to happen at pi. And there was a minimum at 3 pi over 2. It's now going to happen at double that, at 3 pi. So which means your graph is going to look like this. Okay, it's got stretched. And similar thing on the left hand side.